Hey everyone, and welcome. Today, we're diving deep into one of the coolest concepts in artificial intelligence, Q-learning. You've probably heard of it, and it's this incredibly powerful idea that lets machines figure things out all on their own through pure trial and error.
So, to get us started, picture this. You drop a brand new robot into the middle of a maze. It has no map, no instructions, just one simple goal: get to the exit. How in the world does it learn the best way to go? How does it avoid just wandering around in circles forever? Well, that's the exact puzzle that Q-learning was designed to solve.
So here's our game plan for today. We're going to start with the basics. What even is Q-learning? Then we'll look at the algorithm that makes it all tick. We'll see how you can tweak the agent's personality, walk through a real example step by step, and then we'll see it all come together in the end. All right, so first up, what is Q-learning? You can really think of it as giving our learning agent, our little robot, its own internal map and compass to navigate a world it's never seen before. Okay, that's the textbook definition, but what does it actually mean? Well, at its core, Q-learning is all about learning from consequences. An agent tries something out in its environment, it gets either a reward or a penalty for what it did, and it uses that feedback to make a smarter choice next time. The whole point of the game is to get the highest score possible in the long run. And this formula right here, this is the engine that drives the whole thing. I know, it looks a little scary, but let's break it down. It's just a set of instructions for the agent to update what it knows. The goal is to figure out the Q value. Think of it as the quality of taking a specific action A when they're in a specific state S. To do that, it looks at the immediate reward it just got, R. And then, this is the really clever part, it peeks into the future. It looks at the best possible move it could make from its new spot. That future reward is toned down a bit by a discount factor, gamma, and the whole update is balanced by the learning rate, alpha, which decides just how much this one new experience should change its mind. Okay, so we've got the formula, but how does an agent actually put it to work? Well, it follows a really simple, repeatable process. Let's check out the rules of the road. First things first, we give our agent a Q table. Just think of this as its memory, or maybe a cheat sheet. It's a grid that's going to hold a value for every possible move from every possible location. At the start, it's all zeros. The agent is a total blank slate. Then, it just repeats this simple loop. It looks at where it is, it picks the move, it does it, and it sees what reward it gets. Then, using that formula we just saw, it updates the value in its Q table for that specific action. It just does this over and over and over again. Observe, act, update, getting a tiny bit smarter every single time. Now, we don't just throw our agent into the world and hope for the best. We actually get to play around with its personality a bit by tuning two really important dials that control how it learns. The first dial is the learning rate, alpha. This is all about how much the agent trusts new information. If you set alpha high, it's kind of forgetful and only cares about what just happened. If you set it low, it's more cautious and sticks with what it already thinks it knows. The second dial is the discount factor, gamma. This one is all about foresight. A high gamma creates a patient agent that's willing to make a few boring moves now to get a huge reward later. A low gamma makes the agent impulsive, always grabbing the closest, fastest reward it can find. You can imagine how important this is for something like a chess AI, right? You know, to really get a feel for that learning rate, let's do a little thought experiment. What if we just crank that alpha dial all the way up to its maximum, a value of 1? What would that do to our agent?
Well, when we plug 1 in for alpha, the math gets way simpler. That whole first part of the formula that looked at the old Q value, it just vanishes. The new rule is super direct. The new Q value is just the reward you got right now, plus the discounted reward you expect in the future. In other words, whatever the agent used to think about this move is completely thrown out the window.
So what does this actually mean for our agent's behavior? It becomes incredibly reactive, maybe even twitchy. Its learning can be super unstable, because one weird random reward could make it totally change its strategy on a dime. It's like having a carefully made plan and then tossing it in the trash the second something unexpected happens. Now, this could be useful if the world itself is constantly changing, but for most problems, it's a disaster, because you're ignoring all the valuable lessons you've learned before. Okay, that is enough theory for now. Let's actually watch this stuff in action. We're going to see an agent take its very first steps and build its brain completely from scratch. So here's our setup. On the left, that's the agent's entire world. It's a simple map with 6 spots, or states, and the big prize is at state 5. To help it learn, we have a reward matrix. It gets 100 points for hitting the goal, 0 for making a valid move, and a penalty for trying to walk through a wall. And on the right,
That's our agent's brain. It's QTable. And as you can see, it's completely empty. Right now, it knows nothing.
All right, let's kick off the first learning session or episode. We'll put our agent in state 1. From there, it can see it has 2 options, go to state 3 or go straight to state 5. Since its QTable is empty, it has no idea which is better, so it's just going to pick one randomly. We'll also set our discount factor, gamma, to 0.8, which means our agent is pretty good at thinking ahead. So let's say it gets lucky and randomly picks state 5. Jackpot. Now we have to update the Q value for that specific action, moving from state 1 to state 5. The math is the immediate reward, which is 100, plus our discount factor of 0.8 times the best possible reward from our new spot. And since state 5 is the goal, there are no future moves, so that future value is just 0. So our new Q value is a nice, clean 100. And boom! Just like that, the QTable gets its very first number. The spot for being in state 1 and moving to state 5 is now 100. Our agent has just learned its very first and very valuable piece of information. Since it reached the goal, that's the end of episode 1. Okay, time for episode 2. This time, let's say the agent starts out in state 3. It looks around and randomly decides to move to state 1. Now we do the math again. The immediate reward for this move is 0, but this is where it gets really cool. We take our discount factor, 0.8, and multiply it by the best move it can make from its new spot, state 1. And thanks to our last episode, it already knows the best move from state 1 is to go to state 5, which is worth 100 points. So the new Q value for moving from 3 to 1 is 0.8 times 100, which is 80. You can literally see how knowledge is starting to spread through the map. So our agent has learned 2 little things. But what happens if we let it keep doing this for thousands of episodes? Let's jump ahead and see the final product. After running this simulation over and over, the values in the QTable eventually stop changing much. They converge. And what we're left with is this, a fully filled out guide. Every single number in this table now represents the best possible long-term score the agent can expect to get if it makes that move. The blank map is now a detailed treasure map. So now the learning phase is over. It's graduation day. Our agent is no longer wandering randomly. If we put it down in state 2, it just looks at its table, sees that moving to state 3 has the highest value, 64, and does it. From state 3, it sees the best move is to state 1, worth 80, and from state 1, it knows the 100-point move is to state 5. It has figured out the perfect route all by itself. So let's just quickly recap the big ideas. Q-learning is an awesome way for an agent to learn the best actions through trial and error. It uses that QTable as its brain, it updates that brain with a simple but powerful formula, and after enough practice runs, that table becomes the ultimate guide to getting the most reward. You know, it's easy to look at a simple maze like this and think it's just a toy problem. But the exact same logic, trial, error, reward, and updating a value table, is what's used to teach an AI to master a video game, to optimize a massive shipping network, or to control a delicate robotic arm. It really leaves you with a huge question. If we can teach a machine to solve a maze, what are the next great challenges we can teach it to solve for us?